the electrolysis of aqueous electrolytes for Cambridge IGCSE Chemistry. We'll start with the electrolysis of dilute sulfuric acid, which is essentially the electrolysis of water. Look at electrolysis of aqueous salts, anode and cathode rules, and apply that to concentrated sodium chloride solution, and then finish with electrode half equations. The electrolysis of water takes place in the presence of dilute sulfuric acid. Water decomposes to form hydrogen gas and oxygen gas. Can you write an equation for that? Stop, write the equation, come back when you are done. Okay, so 2 molecules of water give us 2 gaseous hydrogen molecules and an oxygen molecule. The electrode reactions involve hydrogen ions and hydroxide ions from water. So we can think of water to a very small extent existing as hydrogen ions and or releasing to a very small extent hydrogen ions and hydroxide ions. Hydrogen ions, of course, being positive, are attracted to the cathode and are reduced. Hydroxide ions are attracted to the anode and are oxidized. Have a go at the 2 electrode equations, the ionic half equations for the reduction of hydrogen ions and the oxidation of hydroxide ions. Stop, come back to check when you are ready. Okay, so hydrogen ions, fairly straightforward. 2 hydrogen ions gain an electron each to form hydrogen gas, H2. Hydroxide ions, on the other hand, slightly more involved half equation. 4 hydroxide ions each lose 1 electron. Oxidation is loss of electrons to form oxygen, O2, and 2 molecules of water, H2O. These 2 half equations need to be known. The electrolysis of dilute sulfuric acid is conducted in a Hofmann voltameter. You may have seen the apparatus here. The electrodes are platinum, inert platinum, platinum cathode, platinum anode, dilute sulfuric acid. The reaction is essentially a decomposition of water. H2O goes to 2 hydrogens and 1 oxygen. Water releases a small number of hydrogen ions and a small number of hydroxide ions. This is greatly increased by adding sulfuric acid. So dilute sulfuric acid has a much higher concentration of hydrogen ions. So what happens at the cathode? What happens at the anode? Can you write half equations for the 2 changes to produce hydrogen and oxygen? Stop, come back when you are ready to check your equations. Okay, so at the cathode, hydrogen ions are attracted to the cathode. The cathode is negative, hydrogen ions are positive. Reduction takes place. They gain 4 hydrogens gain 1 electron each to make hydrogen gas. At the anode, you are expected to recall that 4 hydroxide ions each lose an electron to give oxygen and 2 waters. Now you'll notice that in the electrolysis we get 2 volumes of hydrogen and 1 volume of oxygen, and that is reflected in the volumes of gases collected. So at the anode we collect around about half, or it should be theoretically, half the volume of oxygen compared to the volume of hydrogen at the cathode. We'll now look at the electrolysis of aqueous salts. So those are salts, ionic compounds dissolved in water, for which there is a cathode rule and an anode rule. So When an ionic compound, for example, potassium chloride, dissolves in water, aqueous ions are formed. So the giant ionic lattice dissociates to form potassium ions and chloride ions that are free and mobile. However, we have water present. So water also breaks down to form ions to a small extent. We have water forming hydrogen ions and hydroxide ions, as explained in the electrolysis of water on the previous slides. So therefore, in aqueous solution of a metal chloride, 4 ions are present. We've got 2 positive ions, the metal ion and the hydrogen ion, and we've got 2 negative ions, the chloride ion and the hydroxide ion. So we're going to have to make choices between which positive ions are discharged at the cathode and which negative ions are discharged at the anode. So continuing with the example of potassium chloride, aqueous potassium chloride as our metal salt, the cathode attracts positive ions present in solution. So there are 2 types of positive ion, hydrogen ions from water and potassium ions from the salt. So we've got hydrogen ions and potassium ions. Both are potentially discharged, that is, both potentially react at the cathode. So we need a rule to decide which one will react. The rule is the less reactive element ion is reduced. So hydrogen is less reactive than potassium. I hope you recall potassium is a pretty reactive element. So the less reactive element when we compare hydrogen and potassium is hydrogen. The equation, therefore, is 2 hydrogen ions plus 2 electrons form hydrogen gas. The less reactive element ion is reduced at the cathode. The potassium ions remain in solution. At the anode, the negative ions present in solution are attracted. So for aqueous potassium chloride, we have hydroxide ions from water and chloride ions from the salt. Now the rule for the anode is that oxygen is formed from hydroxide ions. So we should be familiar with this half equation. 4 hydroxides, each losing 1 electron to give us 2 waters and oxygen gas. However, we also have the presence of chloride ions. So the anode rule has an exception. O2 is formed, oxygen is formed from hydroxide ions unless a halide ion is present. So in the presence of a halide ion, chloride, bromide, iodide, the chloride ion reacts at the anode in preference. So 2 chlorides are oxidized by the loss of an electron each to give us chlorine gas. However, the halide ion must be present in high concentration for this exception to be seen. But let's look at the electrolysis of concentrated brine, that is aqueous sodium chloride solution. You may have seen this demonstrated in class with the Hoffman voltameter in use again. So cathode and anode. What would be the product at the cathode? What would be the product at the anode? Can you predict the 2 products at the anode and the cathode? Well, at the cathode, the less reactive element ion will be reduced. So we've got sodium ions or hydrogen ions from water. Hydrogen is less reactive than sodium, so we get hydrogen gas at the cathode. At the anode, we'll get oxygen from hydroxide ions unless a halide is present. Well, chlorine or chloride ions are halide ions, so we will get chlorine. The test for chlorine, you may have seen this as a demonstration, it bleaches blue litmus paper. So we can test the gas here, and we will see that it bleaches blue litmus paper. We get a very small volume because chlorine is soluble, particularly in alkali. So we'll see larger bubbles at the anode surface, and they diminish in size as they rise through the Hofmann voltameter. Hydrogen, on the other hand, is not soluble, so we get a good volume of hydrogen, which can be tested with the lit splint if we collect a sample in a test tube and we get a squeaky pop. However, I've said here there are 3 useful products. Well, we've identified 2 of them. Can you use the equation to identify the third? Stop, see if you can do that. Okay, so chlorine and hydrogen are produced. The third product, looking at the balancing of the equation, is sodium hydroxide solution. Now, sodium hydroxide solution is a useful industrial alkali. So aqueous sodium hydroxide is an industrial alkali. So the electrolysis of concentrated brine produces chlorine and hydrogen as expected. Hydrogen is less reactive than sodium. Chlorine is a halogen, so therefore is formed in preference to oxygen. But a third product is also formed if we look at the balancing of the equation, sodium hydroxide, which is a useful industrial alkali. Here is an exam style problem. We've got 3 solutions: aqueous copper sulfate, aqueous concentrated potassium bromide, and aqueous silver nitrate. Identify the positive ions present, the negative ions present. What would be the product at the cathode? What would be the product at the anode? Stop. See if you can predict correctly. Come back to check your answers when you are ready. Okay, so positive ions present, the copper 2+ from the salt, and don't forget hydrogen ions from water. The negative ions, the sulfate from the salt, and the hydroxide from water. So the product at the cathode will be the less reactive element ion. So copper is less reactive than hydrogen, so we will form copper at the cathode. We'll always get oxygen at the anode unless there is a halide present. Well, sulfate is not a halide, so we will get oxygen at the anode. Concentrated potassium bromide. Positive ions present, potassium and hydrogen. Negative, bromide and hydroxide. The product at the cathode, well, hydrogen is less reactive than potassium, so hydrogen gas will be produced. We'll always get oxygen at the anode unless there is a halide present. Well, bromine is, or bromide ions, are halide ions. So we will get bromine in preference. Silver nitrate. Silver, you may or may not be aware, is less reactive than hydrogen. We've got nitrate and hydroxide as negative ions. We'll get silver, the less reactive element formed at the cathode. And the product at the anode is, of course, oxygen, because nitrate is not a halide. Please note, the concentration of the metal halide solution is an important factor. On the previous slide, we looked at the products from the electrolysis of concentrated sodium chloride. But if we use dilute sodium chloride, then we have sodium ions and hydrogen ions, chloride ions and hydroxide ions. Hydrogen is less reactive than sodium. Everything is standard at the moment, but in low concentrations, the exception of the chloride being discharged does not occur, and we get oxygen. So the anode rule is oxygen is formed at the anode unless halides are present in high concentration. So in dilute sodium chloride, that is not the case. So a recap on electrode half equations in the context of aqueous salt electrolysis. So let's recap on the cathode rule. At the cathode, the less reactive element ion is reduced. Reduction is, of course, gain of electrons. So we've got, for example, a metal ion gaining electrons to form metal atoms, or hydrogen ions gaining electrons to form hydrogen molecules. Which one will be reduced depends on the relative reactivity. Copper is less reactive than hydrogen, so if it was a solution of a copper salt, copper would be reduced. But if we had a more reactive metal, a metal more reactive than hydrogen, then hydrogen would be reduced. The less reactive element ion is reduced. At the anode, oxygen or a halogen is formed by oxidation. Oxidation is the loss of electrons. You need to know the half equation for hydroxide ions losing electrons to form oxygen and water. If a halogen or halide ion is present, then the halide ion is oxidized to form the halogen, as long as the halide is there in high concentration. So here are some exam style problems. Write half equations for the reactions at the cathode and the anode for the electrolysis of these aqueous solutions: copper sulfate solution, concentrated sodium chloride, and silver nitrate solution. Stop, restart when you have your half equations written. Okay, so copper sulfate at the cathode, copper is less reactive than hydrogen, so we'll get copper produced. At the anode, there is no halide present, so therefore oxygen in the standard way is produced. Concentrated sodium chloride, well, again, the less reactive element ion is reduced at the cathode, so in this case that is hydrogen. Halide ions are present, and therefore the halogen is produced by oxidation of the chloride ion rather than oxygen. Silver nitrate, silver is unreactive, so silver is produced, or it's less reactive than hydrogen, I should say. So silver is produced at the cathode. There's no halide present, so oxygen is produced at the anode. Well done for finishing the class. If you need more practice, use textbook questions and then past paper questions. Keep to that order. If you want more classes, look at the course list and links in the video description. If you found the class helpful, please recommend it to a friend. Subscribe for new classes, online assessment opportunities, and exam tips. Please like, and comments are always appreciated. Thank you for watching.